So this is probably the least prepared talk I've ever given. I hope it works at least somewhat. I started doing the talk yesterday afternoon, evening. A little bit more explanation of the technical details of what was announced this morning. And just to start at the beginning, the story goes back to 1915. November 1915, Einstein wrote these 4 papers back in the Preußischen Akademie der Wissenschaften. 3 of them about Relativitätstheory, and the 4th one about perihelion precession of Mercury. The next year, he has a first paper about gravitational waves, June 1916. And then 2 years later, he had another one, because in the first one he actually made a few mistakes. So that's where gravitational waves actually coming from. And here, if you're sitting in the front, you see g mu nu equals eta mu nu plus h mu nu. So it's already there back in 1916. And still being taught in GR 1 or 2 these days. From that, quick fast forward, the proposal to the National Science Foundation, 1989, Vogt, Ron Triever, Kip Thorne, Frederick Raab, Ray Weiss. And here's an image from this proposal where you see one curve, LIGO early detector, and another curve, LIGO advanced detector. And a whole bunch of different sources being indicated here, going from the rather extreme supernova 1987A. If it had converted 1% of the rest mass of a sun into gravitational waves, it would have been shown all the way up here. If it's only 10 to the minus 6 solar masses in a supernova, you would be at this line. And then there are the sources we are more interested in these days, the binary black holes and binary compact objects. So here's a binary neutron star coalescence at 10 megaparsecs, binary neutron star coalescence at 100 megaparsecs, and different black holes. Here's a 100 solar mass black hole coalescence at 4 gigaparsecs indicated. All these compact object binaries follow basically the same strategy. You first have to make them somehow. Typically, you start with stars that go supernovae and leave compact objects behind. Then you need to cook up a mechanism to get the stars close enough together, the compact objects, such that gravitational radiation can take over and actually merge the system within a Hubble time. And precisely how this first step of forming binary compact objects works is still a very open research project in stellar evolution. And that is one of the reasons why the event rates for LIGO are uncertain by about a factor of 1,000. Simply because stellar evolution is so complicated to do. Once you have formed these systems and they spiral in, they start out at low frequency, and as they emit gravitational waves, the orbit gets tighter and tighter, and they pass on to higher and higher frequency. So they make a track here towards higher frequency in this diagram. And the gravitational wave amplitude goes up, but the time the system spends in each frequency bin goes down more rapidly than the amplitude increasing. So in this Fourier diagram, the tracks of the compact objects actually go down, despite the amplitude going up. The length of time spent at each frequency is just winning out. But the truly amazing thing is, in these proposals from 1989, the LIGO noise curve was already completely sketched out. All the noise sources had already been analyzed and put on there as well. And it was already anticipated that there would be an early detector and an advanced detector. And then even here I see there are all these buzzwords that are floating around these days. Here this word reads squeezed light. We had a physics colloquium here a few years ago by Nergis Malvalvala, about squeezed light and using LIGO detectors actually as quantum optics devices. Okay, fast forward another 20 years. The LIGO S5 run was the actual flagship run, the end run of the initial LIGO project. The black curve here is what was proposed in, I actually don't know whether this is identically to the line that was proposed 20 years ago, but this is the line that actually was written down many years before advanced LIGO. And the red and green data sets here are the ones that were actually achieved by LIGO. So dead on, except for this small excess here in the low frequency regime. Initial LIGO set out and did exactly what it had achieved, what it had proposed to achieve, building a detector that reaches a certain sensitivity. And they operated it in double coincidence for taking 1 year of double coincident data, as had been proposed in the earlier NSF proposals that were had been accepted. After the LIGO S5 run, which was the one proposed by to the NSF many years before, it was realized that while one is already working on the upgrade, one can do a so-called enhanced LIGO, where one puts in a few simple improvements and runs again. And that gave a further improvement by about a factor of 1.5, 1.3 thereabouts. So this is not quite as good as initial LIGO was. And after running initial LIGO in this enhanced configuration, these were the basic results left over from this experiment. Initial LIGO didn't it reached design sensitivity. It did not detect any compact binary objects. And from the absence of detections, you could place certain limits on how many binary neutron star coalescences, how many mixed binary neutron star black hole coalescences, and how many binary black hole coalescences can be in the universe. And so the upper limits are indicated in gray here. So these are 90% confidence intervals. And blue was the expected region of coalescences based on astrophysical observations for the binary neutron stars and on theoretical modeling for the other two types of sources. So initial LIGO got reasonably close within a factor of a few, but of very optimistic event rates. But it wasn't really that big a surprise that nothing was seen back then. The numbers here on the left-hand side will come back. These are in per cubic megaparsecs per year. And so later I will be quoting numbers in per cubic gigaparsecs. So 1 cubic gigaparsec is here 10 to the minus 9. 100 cubic gigaparsecs would be, 100 per cubic gigaparsecs would be a 10 to the minus 7. And so the bottom line is, at the end of the day, the event rate is indeed somewhere in this regime here for the binary black holes.
What range of masses was implied by this slot binary black hole?
So this particular one is good old-fashioned 1.4 plus 1.4 neutron stars and 10 solar mass black holes.
No, black hole.
10 plus 10. Okay, LIGO, of course, is not a simple experiment. It's a big collaboration with about more than 1,000 scientists in 15 countries and a large number of institutions. And everything, of course, revolves around the black hole in the center of the Milky Way. And the scientists, the LIGO groups, are scattered all over the world. A big emphasis, of course, in the United States. Also, a significant number of different groups in Europe. Europe plays a double role. There's GEO, the GEO consortium between Germany and England, in the UK. Those are, GEO is a direct member of the LIGO Scientific Collaboration, running their own 600-meter detector in Hanover. And then there's Italy and France, the Virgo collaboration running the Virgo detector in northern Italy. A few groups in Japan. Actually, no groups in Japan because Kakra is not a member of the LIGO scientific collaboration. This may change now, or hopefully this will change now with Kip Cannon moving there just a few weeks ago. Groups in Australia, unfortunately building a third detector in Australia didn't quite work out. A lot of activity in India, where still this is the plan to install the third LIGO detector. LIGO has built from the beginning, advanced LIGO, 3 detectors. So they have the 2 sides. The original plan was to have the third detector also installed in Washington, but it was put in warehouses in the hopes, expectation that either Australia or India manages to get the funding of building another site. And then putting the third detector there just gives so much better sky localization properties. So a big effort worldwide, very sophisticated. So this is a theorist's misunderstanding of what actually happened between initial LIGO and advanced LIGO. And basically, there's 3 improvements I am able to explain to you. And for everything else, we would need more specialized speakers. So at high frequencies, the sensitivity of LIGO is measured by the number of photons that are arriving at the photon detector. The higher the frequency is, the shorter time intervals you need to be able to count the number of photons, the fewer photons you have, the square root of n statistical uncertainty goes up. That's shot noise. And so the way to fix shot noise is to increase laser power. Initial LIGO was running with 10 or so kilowatts of laser power in the arms. Advanced LIGO is currently running at 100 kilowatts and wants to go to roughly a megawatt. At very low frequencies, seismic noise comes in. Various environmental perturbations, from waves sloshing at the ocean 500 miles away, people closing car doors, earthquakes in Nepal, and anything you can think of. Actually, earthquakes in Nepal probably throw the detector out of lock anyway. And so what helps there is to improve the seismic isolation system. And advanced LIGO now has an active isolation system where they measure the ground vibrations and actively correct them with actuators. And inside that, they have a 4-staged pendulum, a pendulum hanging in a pendulum, hanging in a pendulum, hanging in a pendulum. And the combination of the 2 of them manages to attenuate outside perturbations by about a factor of 1,000,000. And so this is what is hoped to eventually drive the low frequency cutoff from order 10 Hertz, 40 Hertz to order 10 Hertz. It's presently not there, it's more like 20 to 30 Hertz. Here at intermediate frequencies, what actually matters is the thermal noise in the mirrors. The mirror substrates have thermal perturbations, Brownian motion in the atoms in the mirror substrates. That moves the mirror surface a little bit front and back in some random way. And if you want to measure a displacement 1,000th the time of a proton, 1 in a billion the size of an atom, that matters. And so what helps here in the middle is to average over a bigger mirror area. And so what used to be 10 kilogram mirrors in initial LIGO was upgraded to 40 kilogram mirrors in advanced LIGO. You make the beams bigger, you can average this Brownian motion over more atoms and beat it down.
Can you explain the spike at 350 Hertz?
No.
Those may be harmonics from the suspension system.
I think, Aaron, you're right. That could be a harmonic from suspension systems.
So the 350 Hertz and the 700 Hertz, those are harmonics for the springs on which the test
Okay.
Called what we call the violin.
Okay.
Yeah.
And of course, there's many other important things going on, which I'm just not qualified to explain. So it would be worthwhile bringing in more experienced LIGO experimentalists again. Okay. Advanced LIGO commissioning worked remarkably well. The instrument locked the first time in 2014. And here you see this succession of noise curves as they improve over a period of less than a year, actually. And you can see the range to the typical binary neutron star went up from 0.5 megaparsecs to 67 megaparsecs. Initial LIGO was at around 20 megaparsecs at the end of the day. So very quickly, within a year of commissioning advanced LIGO, it was more than 3 times more sensitive than initial LIGO. That corresponds to a 3 times further distance reach, and therefore 3 cubed, 27 times the expected event rate. So this, even back then, a year ago, advanced LIGO was already way more sensitive than initial LIGO ever was. So here, this is some of the commissioning runs. And then this is more the noise curve of the first science run, the time span from mid-September to October last year. The sensitivity is still pretty similar to what was here, binary neutron stars to about 7-ish or so megaparsecs. And so the basic setup in extreme simple terms is you have your laser light, you shine it into the interferometer, you have a beam splitter, then a Fabry-Perot cavity where the light bounces back and forth about 100 times. This A increases laser power, and B, it increases the effective length of the arms. So what used to be 4 kilometers, then more like 400 kilometers. And the main sensitivity you have is, well, 400 kilometers divided by C is hundreds of hertz. Oh, and I'm off by factors of 2 because light goes back and forth. Then you collect light back here. Most of the light is, the system is so configured that most of the light goes back out here and hits a power recycling mirror. So that light is also being sent back into the system. And a little bit of signal goes out here towards the photodetector. The 2 LIGO sites are oriented such that they are as much parallel to each other as they can. They have 10 milliseconds light travel time, almost nicely parallel to each other, so they're measuring the same polarization of the light, of the gravitational waves, to allow for better coincidence between the 2 detectors to actually to build up confidence to see something. Okay, and then September 14th, 2014 happened. Here's a power frequency plot for the 2 detectors. And you see excess power first at low frequency in the detectors, and then increased excess power at ever higher frequency. A really beautiful chirp signal, both in Hanford and also similarly in Livingston, Louisiana. Just looking at these plots, you can already figure out pretty decisively what's going on. You have frequencies here in these curves, and you have frequency derivatives, f dot, by just reading off frequencies and reading off times. And if you just take a lowest order post-Newtonian in-spiral, Newtonian gravity with quadrupole formula, you will find that a certain combination of the frequency and the frequency derivative gives you something called the chirp mass. And this is this combination of individual object masses. And so from just this type of plot and reading off f and f dot, plugging numbers in, you pretty decisively see that the chirp mass, this combination here, is at least is 30 solar masses. And if you now work back using the definition of chirp mass in terms of n1 and n2, you find that the sum of the 2 objects that are merging has to be at least 70 solar masses or bigger. It could be bigger if the objects are unequal masses. The chirp mass is minimal for fixed total mass for equal mass systems. The other thing you can already do is that just looking at the frequencies and using Kepler's law, the orbital frequency is the gravitational wave frequency divided by 2. So let's plug in 75 Hertz here towards the end. That gives you a separation of your binary, folding in the 70 solar masses, of about 350 kilometers. So just from these pictures, it is already obvious that you will have a tremendous amount of mass within a very small volume of space. Here are the actual light curves that were also shown this morning. The one from Hanford, the one from Livingston, in red and in blue. Those are filtered. First you take out low frequency and high frequency noise where LIGO that doesn't contribute on those time scales. And then you also filter away known spectral lines of the detector, like the violin modes you were asking about earlier. And then after this reasonably straightforward filtering procedure, you can obtain this type of signal directly from the detector output. The data is public, so in principle you are able now to just download that stretch of detector data and regenerate these plots yourself. On the right-hand side, the Hanford data is overlaid, time shifted by 7 milliseconds, and sign flipped because of the way the detectors are oriented. And you see already really nice and beautiful agreement between the two detectors.
Is the disagreement significant?
No.
So in that stage at the end there, once the ring down has occurred back,
yeah.
So that's sort of an example of the steady state fluctuation.
That's the standard detector
so
noise.
That
Yeah.
is an expression of the different noises that are still in there. Presumably there is, well, I guess it was done, optimal filtering to try and have an idea of how to get rid of that so that it's a prettier signal.
For the real data analysis, of course, LIGO tries to do as near as optimal filtering as possible. It's not easy because the noise is Gaussian and not non-Gaussian and non-stationary. For these plots, my understanding is they were actually generated with rather simplistic filtering, but I might be wrong there.
Probably they were, because I would have expected that it would be much quieter towards the end. And another question along those lines is the non-Gaussianity of the signal. Is there a regime where it's pretty Gaussian so that, let's say the higher frequency oscillations, that's sort of, some of the things that one might see in the time streams from the cosmic microwave background. Things might be quite relatively Gaussian on the small scale, but more long range, non-Gaussianity.
So there's a very long tail of very strong outliers.
Yeah.
And so new detection statistics are actually written down to eliminate those outliers. That's one of the steps that's going on. Okay, so these plots look really nice. And so now the first question is, how significant is this signal, besides looking good? And so this happened basically in the first few days of running advanced LIGO. And because it was so early in the run, the decision was made that we don't want to sit on this until the run finishes in January and then spend another 6 months of analyzing the data. We want to get out this news out quicker. So it was computed how long you would have to run to have enough detector data in order to make a false alarm rate of 5 sigma. This depends on the amount of data you sample because the false alarm rate is estimated via time shifting the data against each other. If you have more data, you can do more time shifts, and that measures the significance of your event more clearly. And it was decided that you need about 16 days of coincident data, which took about 5 weeks to accumulate. And so the announcement this morning is only about this stretch of 5 weeks of data here so far. There's more data collected since then, which is still being analyzed and will be the subject of further papers down the road. And up here in front, roughly on day 2, this is where GW 1915-09-14 happened. And towards the end, there was a second interesting signal, which I will mention sometimes later. This is the range on the y-axis here for systems comparable to the one observed. And so LIGO should have been able to see them out to about 1700 megaparsecs or thereabouts. One detector a little bit better than the other. And you see some variations in the detector performance as the time goes on. All these plots are taken from the papers that were published or made publicly available today. Okay, so the signal was actually found in a few different searches. The very first one is a unmodeled search that doesn't care what type of signals it is looking for. It basically looks for coherent excess power in both the detectors. And again, the way this search measures false alarm rates is by time shifting the data of one detector relative to the other detector. Because if it's a real gravitational wave, it cannot arrive at time differences bigger than the light travel time. So if you time shift, you're guaranteed that you have data where you should not have any gravitational waves in coincidence. So you time shift data, you run your detection analysis on it, and you record how many signals you find in this analysis as a function of whatever you use to determine how good your signal is. And so if you do, say, 1 million time shifts, then you can measure the number of events you would have to roughly 1 part in 10 to the minus 6 per experiment. And this is what you get with the 16 days of data. You can do about 1 million time shifts, and so you can measure events that would happen once in 1 million detector runs. And so the green and the black curves here is what was measured if you're analyzing the time shifted data. You have, at a significance of 12 in this detection statistic, you would find one event in every 10 to the 5 runs. And as you go up further in the detection statistic, it's getting really, really noisy down here. The actual data are these points up here. So you have a bunch of signals that happen often that you find in your detector, and you find the same rate in the time shifted data you determine your false alarm rate with. So all of this is just usual detector noise. You shouldn't worry about it. But once your signal gets significantly away from the lines traced out by the false alarm rate, then you know that you have a rather unique signal that is inconsistent with noise. And I guess this point over here qualifies as rather far away. And simply because by how the number of time slides worked out, this happens to correspond to a false alarm rate of 4.4 sigma or 4.6 sigma, simply because not more data was taken to push this further down. This is the unmodeled search, which made no assumptions whatsoever what type of signal there is. And then there are also these so-called modeled searches, where you use your information that you have, how your signals should be looking like, from post-Newtonian theory, from numerical relativity calculations, and do matched filtering to look exactly for those signals and no other ones. There's 2 such searches that are deployed by LIGO independently from each other. One is called BiCPC, the other one is called GSD-LUL. And GSD-LUL should be a term that should sound familiar to some of you. This is where Kip Cannon spent the last decade of his life at. developing and improving this particular search pipeline here. The pictures are exactly what I've just explained to you. You do many time slides of data between the detectors, run an analysis pipeline, and you find how many, and you count how many signals you find in this time-shifted data. That gives you the background, the number of events that are just noise in the detector. And then you run your analysis on the actual data without time shifts, and you see what you find then. In fact, the way that LIGO does this is they first look only at the time-shifted data until they have tuned the searches, until they are satisfied that everything is tuned as well as they can. Then they run the non-time-shifted data, and they do not retune afterwards. So they try to keep the tuning they try to do the tuning completely before looking at the data in order to avoid confirmation bias. And again, in both searches, you see the same story we just had. A lot of signals at very small significance, consistent with false alarm rates, and an extremely strong signal, that's the one that's being detected. And those two signals here are the identical signals being detected, and it's also the same signal that the burst search on the previous slide had been detected. The model searches, because they know what they're looking for, can go deeper. So these searches actually reach past the 5.1 sigma, where it's no coincidence that this is close to 5, because it was determined ahead of time how many days of data you need in order to get 5 sigma.
So just the background on GST Lao, since it's heavily developed CITA. Presumably it's sweeping over a parameter range that's continuously being applied to the data. And how long does this process take in terms of the compute intensity to try and look at the signals coming in?
So this is one of the reasons for the existence of GSD-LAL. So let me first talk about BiCBC. The way BiCBC works is it takes a week of data. So it runs always a week behind, analyzes the noise properties for this week of data, and uses the analyzed noise properties to define the optimal filter it's going to use in filtering. GSD-LAL was developed to be a low latency pipeline targeted towards neutron stars with the goal of having results within a minute or so you can send them off to telescopes. So GSD-LAL is actually a live analysis with some predetermined power spectral noise density and some other improvements that allow it to actually get an answer in a much shorter time than the signal is long. So binary neutron star signals can be 10 minutes long, 20 minutes long, and GSD-LAL can have the answer 1 minute after. So much before you can actually even do a full Fourier transform on the signal. So a lot of the technology in GSD-LAL were geared towards this low latency stuff. Okay, so we are very confident that we have indeed seen an event. So let's go to the next question, is what have we seen? And let's first make the simple assumption that general relativity is actually correct. At that point, we can do parameter estimation based on gravitational waveform templates computed on general relativity. And this to big parts is, and so here, and this is done with Markov chain Monte Carlo. I'm showing two of the important plots here. On the left-hand side is a projection into the M1, M2 plane. So the more massive black hole has about 35, 36 solar masses. The less massive one about 29. And you see that's quite significant uncertainties. And here's the two-dimensional posterior distribution, where you can see that this line at 45 degrees essentially means that the total mass is better determined than the mass ratio. That's fairly easy to work out if you have a post-Newtonian theory. Because at lowest order post-Newtonian theory, I was showing you the chirp mass formula up here, it turns out in lowest post-Newtonian order theory, only this capital M enters the waveforms, and how the chirp mass is distributed on M1 and M2 doesn't really come in. So the chirp mass is determined to lowest post-Newtonian order. The mass ratio is only determined from higher order post-Newtonian corrections. And so there are always these elongated ambiguity contours. Okay, so those are the component masses. Here is, this goes back to a question that Peter asked this morning. Distance inclination ambiguities. The distance posterior goes from roughly 200 megaparsecs to 600 megaparsecs. And this is very degenerate with the inclination of your system. If you have a face-on system, you can see it emits stronger waves in the direction face-on. And so to get the same amplitude of the waves here on Earth, the system would have to be further away. If it's edge-on, it would have to be about a factor of 2 closer. And this is what you're seeing here. You can either have it face-on. Why this is called face-off, I don't really know. Face-on, face-off. Okay. Anyway, you can either have it face-on and far away, or you can have it edge-on and quite a bit closer. There is some polarization sensitivity that can distinguish between clockwise motion of the binary and anti-clockwise motion. That's why we know that it's actually in this right-hand side of the inclination part, and almost much less likely in the left-hand side of the inclination part. Spins. So at lowest post-Newtonian order, only the chirp mass matters. At the next post-Newtonian order, the mass ratio comes in. And at the yet next higher order post-Newtonian, a certain combination of the two component spin comes in. Roughly speaking, a mass-weighted sum of the two spins, of the spin components perpendicular to, parallel to the orbital angular momentum. And so this is precisely what is plotted here on this axis. A line spin is the sum of the black hole spins parallel to the orbital angular momentum. And you can see from the posterior here that the sum of the two of the components of the black hole spins parallel to L, it must be very close to 0. The green curve is the prior that went into the Markov chain Monte Carlo modeling, and the gray curve is the posterior that comes out of it. So it's significantly more peaked towards 0 than the prior. So you have actual information in the signal that points towards having a very small effective spin.
Where does that prior come from?
That prior is basically chosen to have, it's an assumption of, the assumption of having your black hole spin directions be isotropically distributed in all of the 4 pi, and the length of and the uniform prior on the magnitude of the spin between 0 and 1. On the y-axis here is a measure of the spins tangential to the orbital plane. Those are the spin components that actually cause precession. And you see green is the prior, gray is the posterior. There's essentially nothing we can say about the spins in the orbital plane. We cannot say whether the system is precessing or not. Not particularly surprising for 2 reasons. Reason number 1 is the system is pretty much face-on, and so if you get modulations of your plane, they will be very small because they go like the cosine of your angle, and so you're at the maximum of the cosine. Part 2, the system is the waveform is very short. Precession manifests itself during the in-spiral when you have enough cycles to have actually full precession cycles and get benefit from a lot of modulations in the waveforms. This is such a high mass system that you have very few cycles in band, and so you don't really have the number of cycles you need to measure precession.
Do you know if precessing models were used as parameter estimation?
So these two plots were done with the so-called Phenom P model. Is this already enough?
Yeah.
Okay.
Not for everyone else.
Which is a simplified model not taking into account all possibilities of black hole spins. A second model, the EOB&R V3 model, was also run, but it runs so much slower that there's much less data. But the data that is here is consistent with these plots. And here, yeah.
Take a step back here. How was the science of this managed with such a large collaboration and all of these things that are being run in real time? People saying, look at this. And you've got 1,000 people. How can you organize that to get the information out? It wouldn't be one single telecom, that's for sure. It's really mind-boggling that all of this stuff was, and we had no hint.
You had no hint?
Well, no, that's a triumph of collaboration, except for Larry Krauss. Spill the beans, but it's really quite amazing that you have about 1,000 people. You have this tremendous comparison exercise going on with unbelievable excitement. There was a quotable quote that Vicky Caligara didn't even tell Fred Razio, her husband, about this. And so, it's just amazing suppression of emotion. But I'm just sort of wondering about how, we sort of did it in Planck, to be sure, but it was because of a lot of little smaller scale telecons where this stuff was done.
So LIGO also falls into various groups of people interested in various aspects. And so the typical telecon where actually work gets done has perhaps 20 or so participants. And then on top of the small group of people who actually do work, there's several layers of synchronization and overall project management to make sure everything is actually moving towards a coherent goal. And everybody has been very good in keeping the detection quiet. I fully agree.
But when there's, the hot results, so it's radiating from about 20 people and then it trickles into the 1,000?
Roughly speaking, there's several groups of 20-ish people, yeah.
Anyway, it's a really interesting sociological experiment.
And
Scientific experiment.
And I have about 7,000 unread emails in my inbox. Okay, so not only can you talk about the initial black holes, but you can also talk about the final black holes. And so here are the final mass posterior and the final black hole spin posterior. So we have the remnant black hole is about 62 solar masses, and it spins with about 70% of maximum Kerr.
And in this case, there are no priors shown here. So
In this case,
priors or something like that?
So I don't know what so the priors here would be quite complicated because this is one coherent in-spiral merger ring-down analysis. So the priors are chosen on the initial masses and spins, and this will then carry over into whatever is at the end of the day. But you've remarked this very correctly, Aaron. There is no, I'm running way behind. There is no prior shown here. Instead, what is shown are two different waveform models doing the Monte Carlo modeling as a means to estimate how much uncertainty in the waveform knowledge is and how it impacts the results shown. So the two waveform models in use are these Phenom models and the EOB&R models. And for those people in the know here, the second set of waveforms, EOB&R, is based on numerical relativity simulations done here and in our collaboration. Probably 2/3 of them having been run in Compute Canada systems. This is what keeps SciNet busy. And then you have long lists of numbers that are actually not interesting to look at, but it's a good way of actually highlighting some of the extremely good outreach materials that also have been generated by the collaboration. I'm just highlighting here a GW 150914 fact sheet, and probably still too small to read. What I'm highlighting here is this little box of numbers. Peak strain 10 to the minus 21. Peak displacement of the mirrors 0.002 femtometers. Speed of the black holes 60% of the speed of light. Peak luminosity 4 times 10 to the 56 ergs per second. And we radiate about 3 solar masses in energy in 0.1 seconds. And this then leads to this really nice plot where you have here in gray the waveform as reconstructed from the instrument, and in red the best fitting numerical relativity simulation happens to be an SXX simulation. Up there some nice graphics of how the system looks like. This again actually is data from a numerical relativity simulation. And at that point, of course, I can't resist and show my movie a second time. Black holes happily orbiting about each other. The plane describing the space-time geometry, as Kip Thorne pointed out this morning. The depth is the curvature of space. Colors represent time dilation. Errors represent frame tracking. And up there, the black holes. The northern hemisphere of the black holes are color-coded. This is actually a precessing simulation. It's consistent with the data, but it just shows precession. As you can see, now the black holes, the colored part of them looks towards the observer. Now it's pretty much pointing the opposite way.
Did they begin with spinless holes?
No, this was a simulation with black hole spins of 0.5 or 0.6 thereabouts.
So when you really tune that up, do you see a lot more frame dragging in the first parts?
I would imagine. However, what's plotted here are completely coordinate-dependent quantities. So this also depends on on the special coordinates that the numerical relativity is using. But it looks good.
It look even better with extreme frame dragging.
Yeah. And you've seen this logo a lot. Quite a lot of the banner movies that are being floating around the internet these days are done by our SXX collaboration. Caltech, Cal State Fullerton, CITA, Cornell, AEI in Germany, Oberlin College and Washington State University. So we've grown quite a bit over the years. Okay, is GR right? I guess I should be speeding up a little bit. Here's plot number 1. This is again from the main paper. I had shown you before the top panels here, the actual measurements from the detector. And I also had just shown you the numerical relativity waveforms. And if you subtract the best fitting waveform template from the detector data, this is what remains. So you actually have something that at least visually looks like it's consistent with noise. Another test you can do that was done to check whether general relativity is right, is to compare the masses and spins of the individual black holes about to merge. You can estimate those from the in-spiral part of the waveform only, and compare with the final mass and final spin of the remnant black holes. If you take the entire data front to back to measure final black hole masses, you get this little curve here, which I already showed you earlier in the posterior. If you now only measure masses and spin from the in-spiral, and then use numerical relativity to predict what the final mass and spin would be, you get this big curve, this big feature here. It's quite big because there's so little in-spiral left, but it's consistent with the entire waveform. And if you go the opposite way and only take the ring down and try to estimate quasi-normal modes and read off masses and spin from the ring down, you find this contour here on the left-hand side. And all three of them are perfectly consistent with each other. More about the quasi-normal mode measurements. From the entire inspiral merger ring-down waveform, you can read off the quasi-normal mode decay time and quasi-normal mode frequency very accurately. And if you measure it only data past merger, again, everything fits together quite nicely. If you start measuring only 1 millisecond past peak amplitude, you're still off, indicating that you're not yet in the linear quasi-normal mode regime. If you measure a little bit later, starting at 3 milliseconds and 5 milliseconds, you find good overlap. And the later you measure, the bigger the contours become, because the signal decays away exponentially, so you have less data to work with. Finally, or next to finally, you can take your analytical waveform model and tweak various terms by hand. Let's say I take the 2pn coefficient from the real model and just change it around by 10%, a factor of 2, a factor of 100. So if say the 2pn coefficient changes by more than a factor of 5, then the waveform, this modified waveform would be inconsistent with the observed signal. So these here are bounds on how close to general relativity the various pn coefficients are based on the data that has been observed. And so, as I said, everything here is consistent with just plain old general relativity. And the other point to make is that for many of these post-Newtonian coefficients, the measurements are much more stringent than pulsar timing. Pulsar timing has very, very tight constraints for the low-order post-Newtonian coefficients, because pulsar timing happens at much larger distance and you're measuring thousands of or millions of orbits. But pulsar timing has absolutely dismal constraints on the higher order post-Newtonian coefficients, because the system is so widely separated that higher post-Newtonian terms just don't matter. Whereas here we have, with this system, we have the opposite. It's a very massive system. You only see the last 5 orbits, the last 10 cycles. So we can precisely determine the higher order coefficients.
Do you have any sense of what signal noise you need to get these errors down, say, to the 10% level?
I would imagine those errors are, for a single system, those errors will be proportional, I would guess, to the signal-to-noise error. So you would need significantly louder signals. But because we believe that all black holes follow one and the same theory, once one has many signals, one can do a joint analysis and then presumably gain with the square root of number of events. This is another cool thing I like. If you had a massive graviton, the high-frequency parts of the waveform would travel faster than the low-frequency parts, and so the relative timing between inspiral and merger would be different. That's not observed in the actual signal, and so you can work back and actually bound the difference in propagation speed between the different frequencies, and that way get a bound on the Compton wavelength of the graviton, which is a factor of a few better than solar system tests. Okay, any questions? So I have... Hey, I'm not done yet. I have a little bit more. At that point, I was running out of time and out of energy last night. As I said,
In terms of
Yeah.
the constraint on mass, so if, let's say we had some, I'm not sure how it would work exactly, some kind of effective screening so that you get an effect of gravitational mass on very large scales, but not on solar system. I assume that, I mean, that's one aspect of this which makes it not just better than solar system, but different than solar system in terms of scale. So I would say that's pretty interesting. I don't know if there are, whether there are models that have graviton mass, which is effectively scale dependent. You know?
Yeah, maybe we can discuss it later.
Yeah. Okay, and then there's another fraction in LIGO that really likes to do statistics. And so they did very sophisticated rate estimates of, given the observations, what this implies about the number of binary black hole coalescences in the universe. The simple and conservative answer is somewhere between 2 and 400 per year per cubic gigaparsecs. And here's a more detailed plot that shows probability density of the rate for a few different assumptions of the mass distributions for black holes.
And that will improve rapidly.
And that would presumably improve with further detections quite rapidly, yes. And I think this is the last thing I have, is from the astrophysical implications paper. Given that we now have seen black holes with 30 and 35 solar masses, what does this tell us about the environment where these black holes formed? Well, the blue and the dash curve are from a work by Palczynski 2010. So if the stars you're starting out with have strong winds, too much mass is being blown away, you never make these massive black holes. So this favors the strong wind hypothesis. And even with weak winds, in order to get black holes as heavy as 35 solar masses, you must have a metallicity of at best something like 5% of solar metallicity. So even a single system already constrains both wind models for stars as well as the metallicity of the environment where the black holes were generated. Okay, so today the detection paper was announced, that is already accepted by physical review letters, plus 12 companion papers that are going to be submitted in the coming days and should appear on the archive tonight, and that should already be downloadable from the LIGO site. Also, the detector data itself, a minute of data around the event, is also made public, so you can download the data and make these time frequency plots yourself. Plus an astonishing amount of outreach materials for various purposes.
What again will the policy be on making the data public in future?
So for each detection, a small stretch of data around the detection will be made public with the announcement. And at some point, the noise in between will also become public. And at some later point, the detector output will become public quite quickly. But all of this is tied to the number of detections being made and years, and it's a rather complicated flow chart, decision chart. So I don't remember the details there.
So I guess the point is that in the longer term, you get to the sort of the gamma burst situation where this is becoming almost common.
Mm-hmm.
Yeah. Things become public data.
Yeah. And so, as I said, here's just a list of these companion papers. One about the search without models, just the unmodeled burst search. One about for the model search, a parameter estimation, rate estimates, astrophysical implications, tests of GR, bounds on the stochastic gravitational wave background, a calibration paper, noise transients in the detector, neutrino follow-up, and a paper projecting into the future of how the detector is going to develop and how many events one should expect in 02 and 03. And I think that's what I had. So the summary is just the talking points from LIGO again. First ever detection of gravitational waves, first ever detection of two black holes, first ever test of Einstein's theory under extreme conditions, and the birth of an entirely new field of astrophysics.
Can you say that one of those theories must have said something about scalar tensor theories. Constraints there on.
I'm sure it has.
Right.
The difficulty with scalar tensor theories or any non-GR theory is that you actually would need in-spiral merger ring-down waveforms for those theories. And they simply don't exist.
But it's now compelling that you start doing those.
Yeah.
If you're starting to put GR at the 10% level, then, you know, that's...
Okay. Yeah.
So about 3 solar masses of material got converted into energy in these waves. What's the intuition by which we can understand that 5%?
How does it compare to supernova, for example?
It's vastly more. Supernova is a few percent of the solar mass, emitted over weeks.
Yeah.
So how can you help us understand intuitively why it's not 10% or 1%? Or can it be for different scenarios depending on...
So that number goes up and down mostly with the spin of the black hole. You have your two black holes orbiting about each other, and they will happily orbit in the mid-gravitational waves and get as deep into their respective potential wells as long as they still have stable orbits to orbit about the other one. If you have line spin black holes, you can either view this as the innermost stable circular orbit moving closer in, so you will get more orbits and that more energy emission, or you can view this as, well, the aligned spin system has more angular momentum that it needs to get rid of first before it can merge, and so again it needs to orbit more and will emit more energy. So the 3 solar masses, the 5%, that number depends on the spin of the black holes. It can go up to 10% for aligned spin cases and down to only 2% for anti-aligned spin cases.
So it would be roughly some fraction of the binding energy of the ISCO, no?
Yeah.
Basically. So if you're not spinning black holes, you're already down an order of magnitude or so.
If you trust your ISCO, yes. Since you don't really have point masses if the other object is as massive as your primary.
I have a naive question and a comment. To me, it seems that the ring down is incredibly short. Is there some way to understand how these two humongous things come together and then suddenly they're a single black hole?
So if you do perturbation theory around a black hole, you find a potential well at a distance of 3m. And so anything that's inside this 3m potential well has a very strong tendency to just fall into the black hole and never get away. And so my interpretation is that a lot of the nonlinear distortions happen within that potential well of the common black hole, and therefore most of those things, the distortions, very quickly fall into the black hole and disappear, rather than hanging around for a long time. That the speed of the ring down depends a lot on the spin on the remnant black hole. For near extremal spins, the quasi-normal mode decay rate can be much, much longer. But you need to go up to 0.99, 0.99999. Aaron, you would know the numbers better than I.
So the comment is from particle physics. So you're measuring the relative change in length of 1/10,000th roughly of the radius of a proton, which is pretty much exactly how well we can measure the radius of a quark at the moment with similar sized machines. I don't know if that's something coincidence or
Yeah.
physical significance.
I suspect the size of the machines is simply a function of what one can afford to build.
Well, that's my other comment. I think you've now taken over the record for particle physics in terms of the project, from initial funding to announcement of a discovery. I'm not sure what that means for the future. Anyway, for young people, hang in there.
I sure hope it will accelerate LISA. John?
Yeah, the layperson's description of a static black hole is that something falls in, it can never come out. So black holes don't emit energy, maybe Hawking radiation. So in this case, you're emitting 10 to the 56 terms of energy.
Yeah.
0.3 seconds or something. So how do you explain that like, to the layperson? So suddenly black holes are emitting energy massive amounts at massive rates. How do you explain that to people who are not black holes specialists?
So if you only have a single black hole, what you're saying is perfectly true. You can't reduce the mass of a single black hole, or rather you can't reduce its surface area. You can still extract its rotational energy. For a binary black hole, there's still the way out in that the surface area of a black hole is proportional to the mass squared. Schwarzschild radius is proportional to mass, area is mass squared. So the surface area of the final black hole is way bigger than the sum of the surface areas of the individual black holes. So there's a lot of leeway where you can still satisfy Hawking's area theorem while still extracting energy. And basically now I think you're asking is where does the energy come from? And you can't localize energy, but speaking on the layman's terms, I would say you can say it comes out of the tension of space-time outside of the black holes. Or the kinetic energy, or the kinetic energy of the black hole. So they're moving at 50% of the speed of light. 1/2 times 0.5 squared is still 10% of the rest mass energy.
I understand, like you do the calculation. That was coming
Yeah.
It's not like a one-liner.
Not that I'm aware of, no.
This is how you get energy from black hole.
Yeah.
The entropy argument he made that the shorter radius of a black hole scales with the mass, and in 4 dimensions of space-time, the area goes up like the mass squared. That's the essential reason why there's some entropy left over, if you like. If entropy 1 plus entropy 2, you get a bigger entropy, you can sort of waste something a little bit. I mean, it's not a perfect watertight argument. I'm just repeating what Harald said before. But I like black holes and I like black hole entropy, so I found that argument quite compelling. But that comes from a position of personal bias.
Okay. Thank you very much for your attention.